All right. So far, so good. It's not looking too terrible out anymore. It was super windy this morning, and my power was actually flickering. But the wind for the moment's died down. The rain's coming. Hopefully, we get a good hour and a half. If I start seeing any weird stuff, I may cut the lecture short, just so that I don't have to. I don't want to say this. So I don't have to worry about this not actually getting recorded, because if the power cuts while we're recording, of course, I lose the file. Anyway, so thank you for still showing up, everyone that is here. Remember, test 3 has officially started, so you should find that in the quizzes and tests section of my math lab. You have until Monday the 4th by midnight. You get 2 attempts just like the last 2 tests. Your review is available in my math lab under the homework section. So that's different from test 1 and test 2. Like we said, test 1 and test 2, you did not have an interactive review this time. I built one because I found them, I think you'll find the material slightly more challenging. And I thought you might want to have some practice with it before going into the test. So you actually can, if you need to see the help me solve this, view an example type of stuff, it's there for you in the review. Remember, there will likely be a paper pencil portion that you'll submit in a Canvas for the final. Likely is 90% likely. We'll talk about that on Tuesday. And the final exam is going to take place Thursday, one day only. We will not have class that day because, well, the class time you could be using for testing. I don't know what every single one of your schedules look like, so you may need the hour and a half during our class to take the test. But it is only one day. I cannot extend it because grades are supposed to be due the next day. I've talked about several times, and I still have students emailing me. It's kind of scary how many people don't actually read the emails that I'm sending or that TCC is sending. If you email me your grade request, I'm not going to go based on that. I'm only going based on the official submitted form that goes through Canvas. And again, you were emailed that link. The last thing about the final is that it'll be similar to test 1 through 3 in terms of questions. I'm not going to pull anything out of thin air. So basically, for the first 3 chapters with material, if you didn't see a question like it on the test, it won't be on the final. But then you're still going to get a couple, 2, maybe 3 questions from chapter 4, something like that. I'm thinking 20 to 25 questions. I will give you a longer time limit. I'm probably just going to give it 3 hours, even though that's way more time than anyone should need. But yeah, so all the final details about the final exam, pun unintended, will be discussed next time. All right. So let's get back to where we left off in chapter 4. So last time we finished chapter 3, we did 3.7, which was a pretty short section in comparison to some of the others. Now I know we didn't finish 3.5. I would love for you to take a look at those homeworks for 3.5, but like I said, I'm not going to count that as part of your graded homework for chapter 3. So we covered 4.1. We introduced the idea of an exponential function, that the exponent is now the variable instead of like a polynomial, it was flip-flopped. We tried to understand the basic shapes of them. They have this kind of flattening on one side and very quick growth on the other side. So it kind of looks like a combination of a rational function and a, say, a quadratic or a cubic or a polynomial, just very different on each sides, each of these sides. We also did this with a base of a half. I think that one got pushed down somewhere or deleted in the process. Maybe that was when I think Word crashed. So this is not 100% of the notes. There was an example that's missing right after this one with the 1/2 to the x. Yep, you can see where it crashed because I don't have this connected. So this was originally connected like so. Yeah, that flattening out. Just reiterating some old stuff. And then you get that explosion. Sorry, I didn't go through that point. Let's just move it a little. There we go. Now it's good. And again, we did the 1/2 to the x, and we saw that it looked like this thing instead. It just is a horizontal reflection, in fact, and I kind of explained the rationalization for that. We said that for the graphs of these, we're just going to see some transformations and or shifts. I'm sorry, transformations involving, that was weird. I just got feedback. Oh boy, it's another fun day, right? Transformations involving shifts and or reflections. We did a couple quick examples of that, nothing too intense. Reminded ourselves of the order that you have to do things, or at least basically these first two have to be done in that order and these last two have to be done in that order, but you can actually play around with it a little bit. We talked about the natural base E, that it's a number. We showed the two compounding formulas, which I do not plan on throwing them on the final exam, just as an FYI, but it's still important for you to see. Then we got into the logarithmic function, which we said was the inverse of an exponential function. So we need logarithms to be able to solve exponentials. If you've got a variable in the exponent, there's no normal way of getting it out. Like if you see an addition, the normal way of getting rid of that is subtraction, or multiplication, get rid of it with division. There's no air quote normal way of getting rid of a base and bringing an exponent down. So we had to, because May 11th is a Monday and we are a Tuesday-Thursday class. That would be why. All right, sorry, distractions. Well, not a distraction, a legit question. I don't want to claim it, but was that. So some mathematicians decided to say, hey, let's just call the inverse of an exponential a logarithm, and then let's kind of backwards engineer everything to come up with a system of rules for how these things would operate so that we will be able to solve these equations like 2 to the x equals 17. Because there are some exponential equations like these two right here that you can solve because, well, 5 squared equals x, it's very obvious that 25 is x because we know our exponents. Or b cubed equals 64, we can figure out this base because 64 is a perfect cube, so we cube root both sides. But with something like 3 to the y equals 13, we have no idea how to handle that problem. So we would need logarithms to solve it. And in fact, if you were given this exponential equation, the black ink above it would actually be the solution. So where did we leave off? Example, let's just call it D because it's more of the same. Actually, no, I am going to call it example 2. Convert. So same rule, same instruction as example 1, but instead of giving you something in logarithmic form, I'm going to give it to you in exponential form. And we're going to have b squared equals 81 for A. So we needed to change this into a logarithmic form. And as a reminder, this was the formula to interchange between these two forms. Now, these are not inverses of each other. They represent the same thing. And I gave you some quick little helpful ways of figuring out what one is versus the other, that a number by itself in one form shouldn't be by itself in the other, and that the base is the base in each form. So b squared equals 81, yes, that's an equation that you should all be capable of solving. You take a plus or minus square root of both sides, and you would get plus or minus 9. 9 squared is 81, negative 9 squared is 81, but I didn't ask you to solve, I said convert. So we'll have a logarithm, so let's go that. We know there'll be a log on one side, it doesn't matter what side it is. I saw it on the right side for all those others, so we'll keep it on the right side. Again, sides don't matter. Now the base of one is the base of the other. In the exponential form, the b is the base. It doesn't have to be the letter b, it can be any letter in the world. It's just nice when they match. So that's the base of the logarithm. Then the other thing I said was the thing that's by itself in one form can't be by itself again. So the 81's by itself here, so 81 definitely does not go on the left side. It goes on the other side with the logarithm. So it goes here. It's the inside of the logarithm, meaning that the 2 is the thing by itself now. And that's it. That's the conversion. Does that make it any simpler to understand? No, in fact, in my opinion, it makes it worse, but the point was just to get used to converting back and forth between the two. All right, so with B, we're gonna do 7 to the x equals 100. 7 to the x equals 100. Okay. Well, I definitely wouldn't know how to solve this equation because I don't know what exponent would make 7 to it equal to 100. It would be some ugly decimal value that I would never guess in my life. I could probably, you know, with 10, 15 minutes, get within 1, maybe even 2 decimal places. But there's no real specific way to get that besides trial and error. But we're just converting. So I'll put the log on the right side again. The base in the original question was the 7, so that's the base of the logarithm. The thing that was by itself before was the 100, so it can't be by itself this time, so it can't be on the left side. It has to be inside the logarithm, meaning that the x is by itself. And then these were the answers. So x equals log base 7 of 100, or you could say x equals log of 100 base 7. Both of those are the same thing, just when we verbally say it that way. Now this is actually a solution. X equals, this is just a number. We have no idea what it is off the top of our heads, including your teacher. It's somewhere between 2 and 3. That's all I can say. Probably closer to 2 if I had to guess, but that is a complete guess off the top of my head. So this is just us practicing going from one form to another because it's a very, very, very common issue in here. All right. Properties of logs. And it's kind of interesting because we do some properties, and then I think the next section is actually called properties of logs. It should be called more properties of logs, arguably. So when we first learn about numbers, we like to talk about some of their properties, like if you add a number to its opposite, you get 0, or if you multiply a number and it's reciprocal, you get 1. So here's 4 properties, and we'll show the derivation or the reasoning, not necessarily the derivation of some of them, but not all of them because time. All right, so log base b of b is equal to 1. I think I saw chat, yes. I'm probably only going to have you have mandatory completion of up to 4.1 and 4.2, Corey. I don't want to say definitively that I won't include 4.3, but 4.1 and 4.2 will definitely be required. Thank you for asking that, and I will make note of that in the next class, or at the end of class at least. So I'll make sure to put due dates for 4.1 and 4.2. They'll both be the end of the semester. So hopefully that will signal to people that those are the 2 that are mandatory. Okay, so some properties of logs. If the base matches the inside, then the whole thing is equal to 1. So this is kind of like an identity. Or if you have the log, if your base is b, so that means it can be any number, but the inside's a 1, this is equal to 0. It's another kind of identity. Kind of like how when you multiply something by its reciprocal, it's 1. Kind of like how when you add add an opposite of a number, you get 0. Then there are 2 more properties. This is just a separator right here. Log base b of b to the x is equal to x. So this is a logarithm of an exponential. This is really the defining property of logarithms being the inverse of exponentials. Remember when we talked about inverse functions back in chapter 2, we said if you ever put an inverse function inside of the regular function or vice versa, the output is just the variable, the input variable, typically x. So if you put an exponential inside of a logarithm, as long as their bases match, basically everything cancels out because you are evaluating an inverse of a function, and it just gives you whatever you put into it to begin with. It works the other way as well. If you go b to the log base b of x, again, this is stuffing an inverse function inside of a regular function, so everything cancels except for the input variable. These are 4 extremely important properties. These are very, very important. If I had to rank them in terms of importance, they would all have the same importance. Some teachers would actually say that the bottom right one isn't seen as much, but I would only say that it's seen less in this class. I've seen it hundreds of thousands of times in other places. These are all very important that you have to have memorized. If you are going to the calculus sequence, you will need these with a degree of frequency. So let's prove the two on the left and one of the ones on the right. So to prove, just convert them to exponential form. So for the first one, log base b of b equals 1. If you switch the forms, and in fact, I'm going to do the base of the logarithm in red just so you can see the difference between the base b and the inside b. So switching forms, the base of the logarithm is the red b, so here's my base of my exponential. So this red b will have an exponent. The thing that was by itself before was the 1, so the 1 has to be the exponent, it can't be by itself again, making the black b the inside of the logarithm, the other side, and I think this is very obvious that anything to the first is itself. It's as easy as that. Now, the fun part was for the mathematician that had to figure this out and unravel everything. That's why I put the proof in quotes, because we didn't really prove it. All we did was we assumed it was right, we changed its form, and we got something that made sense. It's not really a proof. It's not fancy. It's a weak proof, but it does show that it's true at least. So that was the first one. How about the one with the 0? Yes, I said that the 4.1 and 4.2 homework were going to be due the day of the final, the last day of class, the 7th. Yeah, everybody, I want to say there's some people having issues. I don't know if it's because of the storm or something else, but it's definitely a lot of fun right now. Where did log go? I converted it from a log to an exponential form. So I used this right here. So we had the property in the logarithm form, and I converted it to an exponential. When you convert it, the logarithm goes away. So let's try the log base b of 1 equals 0. I don't need a different color this time. So we'll change it to the exponential form. So the base is the base. So again, this black b will have an exponent paired with it. The thing that was by itself before cannot be by itself again. So that tells you that zeros has to be the exponent. The inside is the right side now, so 1. And yeah, anything to the 0 is equal to 1. That's an exponential property. Cool. All right, let's do the top right one. We'll skip the bottom right one in interest of time again, but it's a very similar proof. You would just convert it from exponential form to logarithmic form. So let's do a red b again. Base b of b to the x is equal to x. So this was the top right property, property 3, if you will. So let's convert this to exponential form. So the base of the logarithm, the red b, is the base of the exponential. So the red b will have an exponent. Okay. The thing that was by itself before cannot be by itself again. So this x has to be the exponent of the red b. Otherwise, you'd be putting it on the other side. And in fact, let's make that x a different color for emphasis. There we go. Hopefully that'll help you. So it was the red b to the x, the blue x. That's the left side of the exponential. And then we set this thing equal to the inside of the logarithm. The inside of the logarithm's actually got more than one piece though. It's this entire black b to the x. Well, guess what? B to the x is definitely b to the x, so it does work. So again, these 4 properties are very, very commonly seen. We will see them all over the place in this course. You'll see them all over calculus. You'll see them all over differential equations. If you go high enough in statistics, you'll see it in statistics some, but statistics is kind of its own math. It's interesting math, kind of boring in my opinion, but hey, that's why we have opinions. Is it example 1? I should say example 3. Example 3. Simplify. For A, we have log base 3 of 3. Log base 3 of 3. So those are the same number. Let me just kind of pull this back. So for the first couple, at least, you can see the 4 properties up there. Here comes the rain. All right. So log base 3 of 3, it's one of these four properties. Is it the bottom left one? Well, if it was the bottom left one, the inside would have to be a 1. And that's a 3. So nope. It's not either the ones on the right because it's not a logarithm of an exponential or vice versa. It's just a log. But look at this. The inside matches the base. The inside matches the base. This is the first property. It's a terrible looking equal sign. So that whole thing is equal to 1. Because the inside and the base match, it equals to 1. And if you don't trust this, convert this to exponential form. 3 to the first is 3. All right, B. Let's go with log base 12 of 1. What is that? It does not matter what the base is. The base can be any number, well, except for 0. 0 is the only exception. But I wouldn't do that to you. No one does. No one does a logarithm base 0. It's not possible. It's pointless. So 12 does not matter. If that was a 13, if that was a 17, if it was a 2 million, it doesn't matter. What matters is that the inside is a 1. When the inside of a logarithm is 1, the whole thing turns into a 0. That quantity is equal to 0. C, pi raised to the log base pi of 30. That is a pi, that's our base, raised to a log with another base of pi of 30. Probably one of the weirder numbers you'll see in your math life, possibly, unless you're really, really going on to advanced engineering and mathematics or something like that. But it's only weird in this format. So it's not the left two properties, because you've got an exponential with a logarithm. It's actually this bottom right one. But the nice thing is, the base of the exponential and the base of the logarithm match. As long as that happens, everything cancels out except for the argument being the 30. Again, this is like taking an inverse of a regular function. This is like adding and subtracting the same number. It cancels out. All right, D. Log base 2 of 8. And admittedly, this is where it starts to get more fun. Fun means interesting. Interesting can mean challenging. But this isn't too bad. So let's pull back just one more time. There we go. So log base 2 of 8. And you go, well, it's not the first property because the base doesn't match the inside. 2 is not the same thing as 8. It's not the bottom left one because the inside's not 1. It's not the top right one. Notice the inflection in my voice because I'm going to come back to that. Because it's not an exponential. This is log base 2 of 8. So there's no exponent written. You could say anything's exponential with an exponent of 1. So there's an imaginary little 1 implied there. But even still, that doesn't matter because this 2 and this 8 are not the same number. And it's definitely not an exponential raised to a logarithm. So at first glance, it's none of these four properties. But it is actually one of these four properties. What you need to do, and this is very common, is if you can rewrite a number in exponential form, try that. Yes, you will get a review for the final no later than Tuesday. I'm going to try and have it ready by Monday. I'm going to be working on it over the weekend, but I have to do this for all four of my classes. And unfortunately, you are the last in order. So I will hopefully have it done Monday. My fingers are crossed there. All right, so log base 2 of 8, we said if you can rewrite a number in exponential form, try that. Specifically, we're generally looking at the inside. The base, we tend not to need to rewrite, but I'm not going to say you never want to rewrite it. So 8, this is the same thing as log base 2 of. We can write 8 as 2 to the third power. Now, I didn't need to try and figure out if that was 3 to some number, or 5 to some number, or 17 to some number. What you generally want to do is think about the base matching this base. So because this was a 2, that gave me a hint as to what my new base for the 8 should be. I should try and do 2 to some power. And lo and behold, 2 to the third is 8. Because now we can use one of those properties, the top right one. As long as the bases match, a logarithm of an exponential will cancel out everything except for the argument, which is the exponent. So log base 2 of 8 is equal to 3. Again, that is one of the weirder ones at first, but it is very, very common to see. So let's do another one that has some similarity, but an extra layer of challenge. Log base 5 of 1/25. Now, I'm going to spoil this. We are going to end up applying the same property for this problem. We want to try and make the base of the log match a base of an exponential inside. So we see a 5, and then the other number we see is a 25. So you go, all right, well, can I write 25 as 5 to an exponent? Sure, 5 squared. So let's do that. Log of 1/5 squared. But that 5 squared is in the bottom of the logarithm, not the top. And I forgot my base, log base 5 of 1/5 squared. So let's just scroll back up to the property, and it says it has to be a log with a base, and then just a base to an exponential, not 1 over a base to an exponential. Huh. So are we stuck? Well, no, in fact. We have a technique to bring bases from top to bottom or bottom to top of fractions. Traditionally, what we like doing is we'll see a negative exponent and we go, I don't like that. I'm going to bring the base to its reciprocal position from top to bottom or bottom to top and change its sign to positive. Well, right now, we're more worried about having the base in the top no matter what. So we're going to take that positive exponent and change it to a negative exponent. So what we get is log base 5. None of that changes, but my 5 squared I'm going to take from the bottom and I'm going to put it in the top. So that becomes 5 to the negative 2. Again, the 5 has gone from the bottom to the top. There's nothing else that needs to be written in the bottom, so you can say it's over 1, but you don't need to write that. And when you change a base from top to bottom, you change the sign of its exponent. Up until this point, most of the time, we've only been interested in going from negative exponents to positive. But from here on out, there are going to be a lot of times in math where we're interested in going from positive to negative exponents to make things fit a form, to apply a formula, something like that. So now the base matches the base, the log cancels the exponential, the whole thing is just equal to the exponent of negative 2. I love D and E. These are two of my favorite examples from this section, because they are two things that you will see frequently when you're dealing with exponentials and logarithms. Let's do another. 7 to the log base 7 of y. Okay, so let's just eyeball these 4 properties again, which we're supposed to memorize ultimately. Because, while you're doing a take-home test, and you might argue you don't have to memorize them right now, trust me, in calculus you will. And you should be memorizing them in here. So this is a base raised to a logarithm. So this fits more like this bottom right property. As long as the bases match, everything cancels. Now it's possible we would need to rewrite something into an exponential form, but this is a simpler problem. They're already both 7. So the 7 and the log base 7 cancel, and the whole thing just makes a y. If you don't trust any of these, 6 problems, you can take each question with its answer, change the format it's in, and you should get something that makes sense. Something where everything cancels, or the left side matches the right side, that kind of thing. I'm going to sketch. Oh no, I forgot to insert another page. I got to remember to do that. Page. Perfect, cool. Let me just go ahead and give myself a few pages. so we don't have that incident again. And I'm gonna hit save as well because Word crashed on me earlier today. As a reminder, here we go. Here are the graphs for our basic exponential functions. If the base is bigger than 1, we have exponential growth. It goes through that 0, 1. It starts growing quicker and quicker and quicker on the right. It flattens out on the left. Here's the graph for exponential decay, which does the exact opposite. If you were going backwards in time, you'd say you're growing as you go backwards in time, and then it's flattening out or decaying on the right. But we give them the names based on what happens as you go forward in time, as you move right. They had those horizontal asymptotes at a height of 0, and again, they had that 0, 1 point that they all go through, which we used to do our transformations. You also had to do the transformations with the asymptote. Why am I bringing these up? Because now what we want to do is get the graph of logarithms. So as a reminder, because, let's zoom in a little now since I don't need as much, because logs are inverses of exponentials, we can swap x and y coordinates of the graph of an exponential to get the graph of a log. So I'm going to do this kind of small, and then I'm going to put both the exponential and the log in one picture, and then I'll just do the log by itself. So here's the growth if the base is bigger than 1. We go through that point of 0, 1. We have the growth on the right and the flattening out on the left. And the asymptote, which is horizontal. So let's just flip everything about x's and y's. So this point right here is 0, 1 originally. You go left, right, 0 and up 1. So that means when you invert it, that point will be 1, 0. Now, I don't want to have to go through back to the table of values and invert every single one of these by hand, the 1/8, comma, negative, if the base was a 2, that is to say, 1/8, comma, -3, 1/4, comma, -2. I'm just going to think about this more in terms of a reflection. Too far down. Here we go. So we had mentioned previously that another way to think about inverse functions is that they're a reflection about the line y equals x. So there's the line y equals x. So we're going to reflect this graph across that. So this movement that's going right kind of slowly and up really quickly, that means we're going to go right really quickly and up really slowly. So it ends up looking like this. And yes, I know that's not a perfect looking reflection. I'm doing the best I can. Then our horizontal asymptote for the original exponential function becomes a vertical asymptote for the logarithmic function. And that flattening out on the left side now is going to become almost a vertical line as we approach the asymptote. That is how we develop the graph of the log base b of x, if this black graph was the graph of b to the x. And that's if the base is bigger than 1. So exponential functions have rapid growth, logarithmic functions have very slow growth. Exponential functions have a horizontal asymptote of 0 as you go backwards, and again, this is always if the base is bigger than 1. Whereas logarithms can't even go into the negative region of x. They have a vertical asymptote of 0, and then they just stop. And again, if I was a perfect artist, you would be able to tell that the black and the red images are mirror images of each other across that line, y equals x. If your base is less than 1, which was the exponential decay, so we went through the point 0, 1. We had that, again, if you think about going backwards in time, growth on the left, and then the flattening out on the right, with that horizontal asymptote. So that was b to the x, but now the base is less than 1. It also has to be bigger than 0. So now if we take this thing and we flip it about the line, y equals x, this is our mirror. The 0, 1, again, goes to 1, 0. But that horizontal asymptote that was on the right now reflects across the blue line to go above instead of below. And then this rapid growth on the left is going to become slow growth on the bottom. So here's what it ends up looking like. And it can be a little more challenging to see this reflection. That's too flat. Too many times. There we go. There we go. Again, it might be a little tougher to see. It might be a little tougher to see that reflection there, but it is there. So now, without all the nonsense, let's just get the graphs of the logarithms by themselves. So just the logs. Colon. Black. Okay. Scroll. Thank you. So if your base is bigger than 1, we go through that 0, 1 point. Slow, very slow graph, kind of looks like a, so slow growth, kind of looks like a square root graph. And then we have that vertical asymptote of y equals 0. So this was log base b of x, where b is bigger than 1. And again, you can see the red image here is just now the black image here. Same thing here. I'm going to get this red image just by itself. So we have that 0, 1 point again, with slow growth below on the right of that point, kind of like a square root that's been reflected. And then that vertical asymptoting to y equals 0 to x equals 0. I need to correct that over there. I wrote this as a y equals 0. Vertical lines are x's. That's an x equals 0. Please make sure you catch that. That's vertical line is x equals 0, the same as this one. So this is still the graph of log base b of x, but now the base has to be between 0 and 1. Admittedly, we really don't study this type of graph extensively in this course. But I still need to introduce it so that you can see the inverses of both types of exponentials. This is a much more common logarithm dealt with in research and in calculus. So expect to see this one a lot. I don't really want to say you'll never see a base between 0 and 1 for a logarithm and have to graph it, but it's just not as applicable. The main reason it's not as applicable is because it tends to put us into negative values, and for a lot of things that we model in the real world, we're only interested in positive values. Again, I said a lot of the times, not every time. Move it back down, move up to this stuff. All right, give you about 10 more seconds. Remember, you can always go to the video if you miss anything. And you're welcome. Okay. So again, that was how we created the graphs of the logarithms. This was them by themselves. And again, you don't need to memorize some 7, 10, 12, 50 point method, just a basic shape. Slow growth to the right, vertical decaying at x equals 0 to the left. You can shift these, you can reflect these, you can do all of that stuff. In the interest of time, if I had one more day to lecture, we would practice that stuff. I will not test on it. I'll only test on shifting and reflecting exponentials instead of logarithms, but I still need you to have seen these. Now, earlier, I did something that was almost a mistake when we were here. I almost forgot to write my 5 as a base. And you would have gone, well, hey, what's the base? Well, you know how if we don't write an exponent, there's an assumed number? Or if we don't write a coefficient, there's an assumed number? Or if we don't write a 2 for a square root, it's assumed to be a 2? Well, if you don't write a number for a base in a logarithm, there's an assumed number. So let's talk about that. The common log and the natural log. So common log first. The common log is used for when your base is 10. If your base is 10, we call that a common log. We call it a common log because we see it a lot of the times. It's very common. So we don't write the 10 because we see these things so very, very often. I want to write f of x first. Sometimes the undo takes a couple times to actually work. There we go. If you do not see a base written, you are making the assumption that it's a 10 if it says log of whatever. Log of 10, log of x, log of y, log of x to the 70 million. If there's no base written, it is implied to be 10 in this format. Notice I kept saying in that format because there's another one of these. There's the natural log. And this is when the base is assumed to be, natural. Why does that word sound familiar? I feel like there was a context last class. Oh yeah, the natural number e, that 2.71828. So in nature and other things besides nature as well, when we talk about just anything that's compounding continuously, remember that whole snap of the finger, we've seen 10 bajillion bits of growth, it's just they're all so tiny, you don't really notice it in a microsecond, but it relates to the real world tons. So because we see these things so much, especially in nature, they call it the natural, we're going to have a second type of logarithm where we don't write the base. And it looks like this. And this annoys a lot of students at first. It may have even annoyed your teacher the first time you saw it, admittedly, many, many, many aeons ago. But these are two very important things. We deal with tens all the time because we have 10 fingers and toes, typically. So that's why our whole world is based on tens. If we were all born with, say, 17 fingers and 17 toes, we would live in a world where everything was counted in 17s. That's why computers count in zeros and ones or 0 up to F, which is hexadecimal. So you have letters that are numbers because they have, I guess, 2 fingers and toes and 16 fingers and toes. The analogy falls apart there, but you get the idea. There's different ways to count. Nature counts with this letter E. So if you see ln instead of log, if there's no base written, it's assumed to be an E. First of all, you should never use ln if the base isn't E. This is the only time you should ever use ln. You should never be writing ln 7 of x. There is no reason to ever write that. Just write log base 7 of x. Because ln and log are implying the same operator. It's just if you see ln, that is implying, hey, the base should be an E. So guess what ln stands for? Log natural, aka the natural log. English language is one of the few languages that puts the adjective before instead of after. So log natural means natural log. So again, if you never see a base written, it's either a 10 or an E depending on how we spelled out the logarithm portion, log for log or log natural, ln. So let's try this out with example, what are we up to, 4? Yes, example 4. Simplify. For A, we're going to have the log of 10. So I just wrote log of 10. I did not write a base. So we know, because I did not write a base, this number is implied to be 30 million, right? No, 10. So there is an imaginary or an implied little 10 here, and I'm going to erase it. I'm just showing you that, hey, that's a 10 because I don't see a number there. So the log of 10. I don't know what to do with this. I mean, you haven't given us any rules if the base isn't there. No, I technically didn't give you the rules if the base isn't written, but I did give you the rules no matter what the base is. These 4 properties still play out the same whether you write the base or not. So if you don't write the base, it just means, hey, it's 10. So this is log base 10 of 10. The base and the inside match, and if you remember, that was the top left property, which hopefully you still have written down in your notes. That was equal to 1. When the base and the inside match, the whole thing is equal to 1. B. I don't know why I put it there. Doesn't technically matter. B. The log of 1. LOG of 1. So again, didn't write a base. It's assumed to be the number 10. Now, when there's a 1 inside of your logarithm, it did not matter what number this was, whether it's a 17, a 34, or a 10. This whole thing was equal to 0. When 1 is the inside, the whole thing is equal to 0. That's it. C, the ln of e. Doing math without even seeing any numbers. Isn't it fascinating? The natural log of e. So because I used ln, that is implying that there's a number right here. The number that is implied to be here is e. And then these two things match. It's actually the same type of setup as example 4a. So again, because there's an e implied to be here, the base and the inside match, which means the whole thing is equal to 1. It just got very dark in my house. Wrong color. D. This was the ln of e to the 5th. So again, I did not write a base, so it's either 10 or e. Don't flip a coin. Pay attention to the type of logarithm it is. It says, hey, because I wrote ln, that base is implied to be an e. So there's an imaginary little e right here. So we have a base of e with a logarithm of an exponential. Well, as long as the bases match, then everything cancels out, right? Well, this is an e, this is an e, so everything cancels out. And the whole thing is just equal to the exponent, which is that 5. Example e, not the number e. Log of 1,000. So there's no base written because it's an LOG. The base has to be a 10. There's an implied 10 right there, but I don't like keeping it, so because you won't see it written until you write it yourself. So there's an implied 10 right there. All right, well, that's a 10 and the inside's 1,000. Those don't match, so the answer is not 1. The inside's not just a 1, so the answer is not 0. And this isn't the logarithm of an exponential, ... yet. Because we can rewrite 1,000 as a base of 10. 1,000 is just 10 to the 3rd because there's 3 zeros. So we should rewrite this as the log, again with an assumed base of 10, and then the exponential part will now be 10 to the 3rd. Now, because this base is a 10 that you don't see, and this base is a 10, all of that jazz cancels each other out, and you're left with, once again, just the exponent, and that is 3. So the log of 1,000 is 3. Remember I told you that logarithms have very slow growth? This is the 1,000th whole number you can put into a logarithm, and the output is 3. So you're 1,000 numbers down the line and the answer is 3. That is growing slower than any type of radical you can think about. The square root of 1,000, it's not a number you can actually do off the top of your head. The square root of 100 would be 10. That's only, 100 is only 1/10 of the way to 1,000, and our answer is already bigger than the log of 1,000. So while exponentials are very, 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 very quick growth, logarithms are very, 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 very slow growth. I may have mentioned something called the logistic curve in passing last time. So a lot of people like to talk about the coronavirus and how it is going through this exponential growth. And that's only partially true. It's only partially true because it is going through exponential growth at first. But because we have a population cap, there's only so many people that can actually get the coronavirus. Eventually, the growth has to slow down the closer and closer we get to, say, all the people that can get it getting it. So instead of just seeing this explosion constantly, what happens is it explodes for a while, but then it starts to taper off and it flattens out in terms of the total number of people that have gotten it until you eventually just come really, really, really close or exactly hit the maximum. And this is known as a logistical curve. It is a combination of exponential and logarithmic growth, basically. So we don't study that in this course, but it is a fascinating field of mathematics that I love, so I at least like to give an introduction, because pre-calculus is supposed to be an introduction to fascinating concepts. Right, I got a few more to do. We did A through E, so we're on F. Let's go back to the black. The natural log of 1. Natural log of 1. Well, the inside's a 1. It doesn't matter what the base is. So the answer is 0. That was the bottom left property from previously. One last one. The natural log of these, that is to say, of 1 over e to the 6th. That's the natural log of 1 over e to the 6th. All right, well, we have an exponential inside of a logarithm, so the usual idea is to try and get those things to cancel each other out. Well, this has a base of an e, and the implied base that you don't see written here is an e. So if you say this is equal to 6 because that's exponent to 6, that's not right. You're going too quick. This has the same issue that this example had, the 1 over 25 inside of a log base 5. You're going to have to, well, you don't have to do the rewriting. It's already an exponential form, but you need to take that base from the bottom, bring it to the top, which will change its exponent sign, and then all of the stuff can cancel each other out. So we have to do the same thing here. So we need to write this as the ln of e to the negative 6. And I'll write it in parentheses just for consistency, but it technically is not necessary. Now the base is still implied to be an e right there. And the base of the exponential is e, and it's not in a bottom. So we can say this whole thing is just equal to the exponent, which is the negative 6. There are not a lot of good ways to guess the output of a logarithm unless it happens to fit these nice forms. So you can take the log base 10 of 100 pretty easily. You can write the 100 as 10 squared and the answer is 2. You can do the log base 10. So this was the log base 10 of 100 is the log of 10 squared, which is 2. You can do the log of 1,000, which we already saw the work for that. That was the log of 10 to the 3rd, which is 3. You can do the log of 10,000, which is the log of 10 to the 4th, which is 4. You can do the log of 100,000, which is the log of 10 to the 5th, which is 5. look how slow these things grow. It takes an extra factor of 10 to get to the next whole number in an output. And if you ever look at any research, you may actually find some graphs, they'll say that they're done as logarithms. And I'm not going to get into what all that implies for now, but you might see a linear growth, and if it's a logarithm, that actually means that it's growing very, very, very fast or very, very slow, depending on how they're approaching the problem. But the point of this is, all right, if I wanted to say the log of 125, it's somewhere between 2 and 3. I don't really have any idea what it is. I'd say it's probably closer to 2 than 3, but I can't just guess that. I would need a calculator. If the screen just went away, don't worry, it'll be back in a second. 10 seconds maybe. Come on. Won't let me minimize my screen. There we go. And then the Word file. All right. So I've mentioned that you can put logarithms in calculators, but not always. Let's see if these are true. Let's see if our calculator agrees. LOG, oh, right here on my TI-83. If you can't find it on your calculator, Google it. So the log. Now, that just says log. If I type 100, what happens? So that just says the log of 100. I'm going to bet it's probably implying that the base is 10. I got an answer of 2, so that seems to make sense. How about the log of 1,000? 1,000. 3, yep. So my calculator, when I hit the log button, it's assuming the base is 10. Right below it is an ln. If I hit ln of 1, we get 0. If I hit the ln of e, which is the second and then the division key on my calculator, I get that, 1. If I did the ln of e squared, the natural log and the e should all cancel, and this thing should just be a 2, and that works. So you have a log base 10 and a log base e. Guess what? That's it. That's all your calculator can do up front. So maybe you were trying to check this one, this log base 5 of 125th. You wanted to say, well, I got an answer of -2, but I'm not sure. Let me put it in my calculator just to confirm. Well, right now, I haven't taught you the way to put that in your calculator. You cannot create a new base of a logarithm in a standard scientific and graphing calculator. I'm not going to say you can't do it for every graphing calculator, because there are a lot of better calculators than a TI-83. This is ancient technology. But your general scientific calculators, and the scientific calculator, scientific and graphing, they can only handle bases of e and 10 for your logs. But guess what? There's a workaround that we'll learn in the next section that we can guarantee, we can check that log base 5 of 125th is actually -2. So that closes out section 2. Section 3 is properties of logs. Properties of logarithms. I think my favorite moment in class ever was probably, I said properties of logs, and a student started singing What Rolls Downstairs and Over in Pairs Over Your Neighbor's Dog. If you don't get the reference, look it up. It's just silly. All right, so another case of face value. We're going to give you these without any official proof. I'm not even going to do an air quote proof for this. Just take it at face value. Go to your textbook, go to the internet if you want to see proofs for them. These are a little more twisted, admittedly, in terms of actually doing a proof. The algebra is more intense. So we're just going to give it at face value. So I really think this section should be titled More Properties, since we already gave you some properties previously. In particular, these 4 properties, very, very, very important. Some students would argue that that's 12 properties, because you could write these 4 properties without any of the little b's, and then it's implied that those are 10s. Or you'd have to write it on this one, of course. Or you could write these as ln's, and then you'd have 4 more properties. But it's not 12 properties, it's just 4, and then some special cases of them. If you need to write out the special cases separately, you can, but these four take care of everything. So I think that's good enough. But you've just got to remember, if the base matches the inside, the answer is 1. If the inside's a 1, the answer is 0. If you got logs of exponentials or exponentials of logs, if you can make the bases match, or if they already match, the answer is the exponent or the inside of the log, whichever the case is. So 4.3, more properties of logs, first up being the product rule. The product rule says that, I'll keep it in red, log base b of a product, some m times n. It doesn't have to be letters m and n. This is equal to the log base b of m, then a plus, and another log base b, and then of the n. Hey, Rambo, it's okay. My dog doesn't like storms. He just came to greet me and get under my feet. Okay, so that's your product rule. We call it a product rule because it's the product of a single logarithm. You can actually separate this into an addition of two different logarithms, but the bases have to be the same. You can't make the base of one a 7 and the base of the other a 9. They have to all agree. Next up, we have the quotient rule. And this one follows completely logically, or logarithmically if you want a terrible pun, to the product rule. A product led to a sum, so guess what? A quotient, a division, ends up leading to a subtraction. These are very, 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 very important. Those colors don't clash too much, I hope. You are supposed to memorize them. You will see them littered throughout calculus, et cetera, usual spiel. So when we're dealing with logarithms and there's multiple arguments, multiple numbers, multiple variables inside of it, or separate logarithms, there are times when it's better to have separate logarithms. There are times when it's better to have just a single logarithm. It depends on what your goal is, and math typically works as a grass is always greener. What you see is usually what you don't want. So if you see the product version, you need to probably separate it as a sum, and vice versa. If you see the sum of two, you combine it as a product. Now this rule does not work the other way. A log of a sum is not a product of different logs. So please note that this does not work the other way around. I can't do, and I'm going to erase this, but you can't do it, and I don't want to have it stuck on here. I can't write with a highlighter. So the log base b of m plus n inside of a single one, this is not the same thing as the log base b of m times the log base b of n. Again, this is complete trash. I'm going to erase it. And the same goes for the quotient rule. You can't flip-flop which one's a difference and which one's a quotient. It only works one way. The proof, again, you can kind of convert these things to exponentials. It's a little weird. It's not terrible, but let's just take it at face value and try it out. So example 1. How are we doing on time? 30 minutes. And we're going to expand. So the left side of these is the condensed version. In fact, let me just give myself a little more space. So just a little more space. So the left side is the condensed version. The right side is the expanded. Condensed means you don't have to take up nearly as much space. Expanded means you get the picture. Now we'll do example 1. And the instructions were expand, I believe. Yes. Expand your mind, expand your logarithm. And we're going to do log of 4x. Oh, Mr. Beckner, you forgot to write a base. No, I didn't. Means the base is a certain number, 10 or e, in this case, 10. So to expand, this is a product. This is 4 times x. I didn't write a dot in here originally, but for emphasis, I will. You don't have to have this in parentheses. You don't have to have all these extra little details. Just by writing 4x, that says that 4x is inside the logarithm. If I wanted the x outside the logarithm, I'd have to do this, which is all kinds of weird, but I'm not saying you never see it. All right, so this is a log of a product. So for some reason, maybe we have a reason to expand this besides our teacher just saying expand, but we're just practicing that for now. So the base is a 10, so we're gonna make 2 logarithms with a base of 10, where the first one will have the first factor and the second one the second factor. In other words, don't overthink this, it's the log of 4 plus the log of x. And for now, that's all we're doing. I like introducing this problem because this is not technically the simplest form of the answer, but all I said was expand, so at least it still applies. We're going to circle back to this problem later to actually show what the true answer to this is in simplest forms. In simplest form, not forms. B, let's do the log of 100. Y. So base, once again, is implied to be a 10. You're going to see me do lots of logs and ln's because bases of 10 and e are the most common in the world. Okay, so that's 100 times y, so we can separate this as a sum of 2 logs. Log of 100 plus the log of y. Now, if you stop here, you would get an incorrect answer because this is simplifiable based on rules we've been taught thus far. The log of 100 is simplifiable. So I'm just going to drag the log of y along, but you might say, well, how do you simplify it? This base is a 10, this is 100. Well, I literally did that example earlier in this red right here. You just got to make that 100 a 10 squared, then the 10s and the logs all cancel and you get just a 2. That's that top right rule or top right property from the previous section. So I'll show all that work though, don't worry. So that's the log of 10 squared. Remember, if these don't match, if you can't try a property, try rewriting them with common bases. So that base was a 10, so I tried to write 100 as 10 to some power, which is 10 squared. Then our plus log of y, but this log of 10, sorry, log base 10 of 10 squared, everything cancels except the exponent. So the first term doesn't even have a log. And let me tell you, this is the #1 mistake that students who have decent knowledge of logarithms, but not perfect knowledge, this is the #1 mistake they make. They stop here, and then they get it wrong. That is not the answer because the log of 100 is simplifiable. So you have to be on your toes. When you see numbers inside of logarithms, if it doesn't immediately use one of those properties, make sure that you can't rewrite that as a matching base because then you could apply one of those properties. All right, C, the natural log of e over, let's do z. That's a z in the bottom. Remember my z's, I put a line through the middle. I saw a question. Could we not have made the 4 a 2 squared in the previous example? So, Jonathan, that is an excellent observation, and that is exactly what we want to do later. So what someone just asked, and I didn't want to mention it, but since someone did, I will now. This is going to involve what we'll circle back to later. 4 is 2 squared. Now in B, it was beneficial to us because when we wrote 100 as 10 squared, the bases matched. So all that jazz canceled. If you write 4 as 2 squared, the base is 2, but the base of the logarithm is 10. There is no way to make a 4 have an exponential base that matches 10. So that's why for now writing this as 2 squared isn't helpful, but later when we learn another rule, another property, we will want to write that as 2 squared and it will help us simplify it. So that is a great observation. And again, we'll circle back to that. All right, so back to C, the natural log of e over z. So because that's a division, that's the quotient rule. We're going to separate that as a subtraction. Now, I want you to pay attention to the m and the n's placement in all of this because it's important. The m was in the top of that fraction, and it is then a positive logarithm. I didn't write this, but there's a little plus sign here, imaginarily, right? So the m came from the top, and that makes it a positive logarithm, whereas the n was in the bottom, and because the n was a bottom, that's what makes this a negative logarithm. And guess what? That relates to previously we were bringing bases from the bottom with positive exponents to the top and making them negative exponents. It has something to do with that. So again, anything that comes from a top is a positive logarithm when separated, when expanded. Anything that comes from a bottom is a negative logarithm when expanded. All right, so natural log of e over z. The e is in the top, so that's a natural log of e. That's positive. The z is in the bottom, so that should be a negative logarithm. So the natural log of z with a minus preceded in front of it. So that's the expanded version. And if you box it up, it's wrong. Another one of those. A lot of students make it to this point, stop, and then they made a mistake because they didn't simplify as much as possible. The natural log of e, remember this little base right here, we don't see it, but it is e. They match, which means that whole first bit just turns into a 1. Not a natural log of 1. Remember, those properties were about getting rid of the natural logs. So just like with b, we're able to completely eliminate a logarithm from one of the terms. Maybe that's a reason to be expanding things. Maybe being able to do this is helpful. If I were asking you to graph this natural log of e over z, this is exactly what you would want to do because it gives you a shift and a reflection. This is a vertical shift of up 1 and a vertical reflection because all those are outside the core. Whereas how would you know how to graph the natural log of e over z? We know how to graph logs of x or whatever letter, a log of y, a log of z, but not if the z's in the bottom. I didn't tell you how to do that. Well, it turns out it's a shift and a reflection. All right, D. So that's one thing that expanding is good for, it's graphing. Also, when you get to calculus, when you have to do things like derivatives and integrals very often, it's helpful to expand logarithms as well, but that's not for us. Not today. Log base 2 of 4x over yz. Again, that's another z in the bottom. So this has got more than 2 things inside. I didn't tell you what to do if there's more than 4 things inside. That doesn't matter. All these rules say is if you have a multiplication, separate them with an addition. If you have a division, separate them with a subtraction. So because I got multiple bits in the top, multiple bits in the bottom, it doesn't matter. Anything that comes from the top is going to be a positive logarithm. Anything that comes from the bottom is going to be a negative logarithm. Now, I'm going to spoil something up front. I'm going to write this incorrectly at first. I'm going to do most everything correctly. I'm going to be missing a detail that I'll put in later. So I'm going to pretend to make a mistake right now. So log of 4, the 4 is in the top, so that's a positive logarithm, plus log of x, the x was in the top, so that's a positive one. The y and the z came from the bottom, so they should be minuses. Minus log of y, and then a minus log of z. So there's a mistake in here. The mistake is the original log had a base of 2. And a lot of people get, oh, these are all 10s and e's, all 10s and e's, all 10s and e's. So then when you see the 2, you just drop it. No, these are not 10s. They're supposed to be 2s. They all have to match. You have to be consistent with what the original base was for this. Now, when your inputs, when your argument's a variable, the x, the y, the z, you can't do anything to these last 3. But look at this first one, log base 2 of 4. Someone mentioned earlier, hey, 4 is 2 squared. And it didn't benefit us in that A problem because the bases didn't match, but it will here because they do. And again, when I say don't benefit, again, that's for now. We'll learn something soon. So let's rewrite that as the log base 2 of 2 squared. And I'll put that in red to show you what I changed. This was the only thing that changed. Everything else stays the same. So log base 2 of x minus log base 2 of y minus log base 2 of z. And the reason we do that is because if we hadn't, we might have boxed it up and it was wrong, because log base 2 of 2 squared, all of this stuff, because the bases match, cancel, and you just are left with the exponent, which is that red 2, outside what I circled. But then we have the plus log base 2 of x minus log base 2 of y minus log base 2 of z. That is our answer. So these 4 examples were us practicing expanding logarithms that had products or quotients inside of them. There is one more property that pairs well with these, and it's the power rule. So we have the product rule, we have the quotient rule, and now we have the power rule. And the power rule states that, and again, once again, face value, no proof, the log with a base of something with an exponent, and we'll do P for power. I don't want to use E for exponent for obvious reasons. So if you have a logarithm, no matter what the base is, if inside of it it's exponential, if the base of the exponential and the base of the log don't match, so these two things don't match. This is a B, this is an M. So this is kind of like that scenario with the log base 10 of 2 squared that's inside of this. What we can do is, and this is really, really cool, we can bring the exponent out front as a multiplier of the log. So that's P, not plog. That's P times the log base B of M. So this exponent has been brought out as a coefficient. If I space, is it going to mess anything up? It doesn't. Good. So the exponent has been brought out as a coefficient. The left side is the condensed version. The right side is the expanded version. Now, the condension and the expansion of these is pretty obvious, I think, because this looks like a lot less space condensed. This looks like a lot more space expanded. I don't really see a reason why this one's condensed and why this one's expanded. Condensed means you have as much stuff inside of a single logarithm as possible. That's the true meaning of condensing for logarithms. It means you have everything possible inside of it. So the expanded version, there's something that could be in it, but is not. Now again, there are times when expanding is beneficial. There are times when condensing is beneficial. It depends on the scenario we're thrown in. Right now, we're just practicing how to go back and forth. So far, we've only expanded and none of this at all. So let's practice that. So example 2. Expand. Expand your logarithm. We got the log of x to the 4th. The log of x to the 4th. So to expand this means we don't want to see any exponents inside the logarithm. Now, we would first try and say, oh, well, if the bases match, then everything cancels and the whole thing is just equal to 4. But this base is a 10, this base is an x. They do not match, so that property from the last section does not apply. However, we have a new property that we can use, which I want to highlight like the rest. So what we're able to do is take this 4 and bring it out front as a coefficient, and then everything else just stays the same. And that's it. That's the expanded version. Now we have just a log of a number or a log of a variable without an exponent. Having exponents inside of logarithms complicates things. Having just a number times a logarithm, that's a lot simpler in terms of a concept. But again, just because the left side is more complicated doesn't mean it's not useful. It is quite often useful. Let's do another one. Let's do the log of 4, b. Oh, well, this doesn't apply. I don't see an exponent. Well, you don't see it, but you certainly can write 4 as 2 squared. I wonder if anyone's picking up where we're going with this. So that 4 we can change as 2 squared. And in fact, I'm going to do the exponent in blue for emphasis. So when you have a logarithm of an exponential, if the bases don't match, see this base right here is a 10. They don't match. But that doesn't mean we can't do anything necessarily. We can take the exponent and bring it out front. So there's our 2, there's our exponent 2. And then we have our log of 2. Now, in terms of numerical simplification, this is simpler in the same way that a square root of 8 is simpler by writing 2 square root of 2. Or a square root of 50 is simpler by writing 5 square root of 2, because there are things we can do with 5 square root of 2 that you might not be able to do with the square root of 50 if we're trying to combine it with other stuff maybe. So this is what makes example, was it 1a? Yes, 1a simplifiable. So going back to 1a's answer, which was log of 4 plus log of x. Well, now we know the log of 4 is 2 log of 2, so we can rewrite this as 2 log of 2 plus the log of x. It doesn't look simpler, but in terms of mathematical operations, there would be things you can do with that one that you can't do with log of 4 necessarily. Often. Not every time, often. All right. C. The natural log of 7x to the 4th over y to the 3rd. This is combining everything we've seen in the section now, the product rule, the quotient rule, and the power rule. So we're going to have to make several logarithms. We're going to have to take exponents out. You want to do the exponents last. You need to handle the separation of pluses and minuses first, because with 2 exponents of 4 and 3, which one goes in front of the logarithm? Well, honestly, neither, because there's also an exponent of a 1 right here that you don't see. And if you got different exponents, you can't bring it out. You can only have everything raised to a single exponent. So let's separate this into multiple logarithms. The 7 and the x to the 4th come in the top, the y to the 3rd is in the bottom, so the y cubed is a negative logarithm. So this will be the natural log of 7 plus the natural log of x to the 4th minus the natural log of y to the 3rd. 7, I don't really think we can write that as a base besides itself. So that's as far as we can take that. If it was an 8, we'd have to change it to 2 cubed, because then we could take the 3 out front. If it was 100, we could write it as 10 squared, and then the 2 could come out front. But the second and third logarithms have exponents, and we can bring them out front. So that's a plus 4 natural log of x minus a 3 natural log of y. And that is as far as we can take that one. One more like this, for good measure, the natural log of 100 over e to the 3rd times x. So again, we're going to have to handle the exponents last in this process. So that's a natural log of 100. 100 was in the top, so that's a positive. Minus the natural log of e to the 3rd, because it was in the bottom, minus a natural log of x. Okay. Well, the natural log of 100, we can't simplify just that, but we can rewrite the 100 as 10 squared. It may or may not benefit us, right? It probably will. So there's the natural log of 10 squared minus the natural, let's leave everything else the same, natural log of e cubed minus natural log of x. Now let's handle the exponents. So the 2 and the 3 will come out front. There's nothing to be changed with the x. There's a 1 here, bringing a 1 out front. Doesn't really change anything. Oops, too far to the right. So that would be 2 times the natural log of 10 minus 3 times the natural log of v minus the natural log of x. Natural log of 10, we can't do anything with that. The bases don't match. E doesn't match with 10, so that's it. Some people say, oh, okay, well, we're done now. Nope. Look at that. The 3 doesn't have any effect on anything, but the natural log of v is simplifiable. Remember that the natural log of v is 1 because the bases in e, they match, so the whole thing basically cancels with a factor of 1. So this would be equal to 2 times the natural log of 10 minus 3 times 1 minus the natural log of x, which is just 2 natural log of 10 minus 3 minus the ln of x. And that's our answer. Now, I want to show something else. I want to show this problem done a different way, starting right here. So starting right here, the ln of 10 squared minus the ln of e to the third minus the ln of x. Now, in the black ink, I took all the exponents out front. I didn't have to do it that way with this middle term. The first term, yeah, you have to. There's a 2, there's your ln of 10. You have to do the first one this way. But this middle one, the bases match. So you don't have to take the 3 out front and then say the natural log of e is 1. You can use that top right property from the previous section. If the bases of the logarithm and the exponential match, the whole thing is just equal to the exponent, which is 3. So then the minus 3, then the minus ln of x. The same answer. What I love about this example and why I always do it is it shows that these properties are real. They do actually function properly. Again, I never did any proofs, but I feel like seeing that one both ways just gives us a little more faith that this stuff does run accordingly. What do we have? 7 minutes. Let's do the next 1 or 2 examples and then we'll probably be done. So we did a ton of expanding. Now let's go the other way. Now let's condense, because again, there are times when we want to expand, very often in graphing, very often in doing calculus, which is derivatives and integrals most often. But when we want to solve equations involving logarithms, most of the time what we want to do is condense them. We only want to see a single logarithm so that we can then change it to exponential form, something we're more used to seeing. At least that's the usual affair. All right, so example 3, condense, obviously, condense. Let's switch my color. I didn't mean to do that in blue, not that it matters. Log of x plus the log of y minus the log of 3. So we got a problem. Maybe we were trying to solve this equation or analyze it or something like that. It's not actually an equation. I didn't write it that way. But maybe there's a reason we want this to just be a single logarithm if we can make it a single logarithm. Notice I said if. Because in order for that to happen, the bases all have to match. Well, that's a log base 10, that's a log base 10, that's a log base 10. So yes, we can condense this into just a single logarithm of some products and quotients. There were no coefficients, so there'll be no exponents here. The x and the y came from positive logarithms, so the x and the y go in the top. The 3 came from a negative logarithm, so it has to go in the bottom. And believe it or not, that's it. That's the answer. It's a pretty easy one to start with. Again, because the x and the y were positive logarithm terms, the x and the y go in the top. Because the 3 was a negative logarithm term, it goes in the bottom. If you call this a minus, if you brought that up as an exponent, now you've got an exponent of -1, which takes the 3 from a top to a, you guessed it, bottom. That's why it works. Next up, 6 times the log of x minus 4 times the log of y, probably, yes. 6 log of x minus 4 log of y. So when we were expanding, we needed to do the exponents last. Everything's flip-flop now, so we have to do the exponents first. What exponents? The 6 and the 4, these coefficients. When we're condensing, the coefficients become exponents. So this is the log of x to the 6th. The coefficient goes up as an exponent, minus the log of y to the 4th. Again, the 4 came up as an exponent. You can take the minus with it, but then you'll have to do your negative exponent rule. It's just more work than it's really worth. Now, because there's no coefficients, you can only contract these into a single logarithm when there are no coefficients written. That actually just means they have matching coefficients. So it's implying they're both 1s, but they could both be 2s, they could both be 3s, they could both be 5s. It's a little annoying to deal with because we really want the coefficients to be exponents. But there's some shades of gray there. But anyways, once you don't have coefficients, this is when you condense the logarithm. So just a single logarithm, both the bases were 10, so we can do this. The x to the 6th, that's a positive logarithm, so it'll go on the top. The y to the 4th was a negative logarithm, so it goes in the bottom. And that's all we can do. We have enough time to do C. We do have enough time. I can hear you groaning already. 3 log of 2, I'm kidding. That's my dog snoring. Minus 2 log of 5, last problem for the day, I promise. Plus 4 log of x. Again, all these bases don't have to be 10s. They can be different bases, and that means, well, first of all, they don't have to all be 10s. They can all be 7s. They can all be 31s. They can all be e's. They can be any number they want. As long as they're all the same, you can condense them into a single logarithm. But there are weird, wacky problems where they're not all the same, and then you'll still have 2 or maybe even 3 logs in the answer. Let's handle the exponents first. Bring the 3, the 2, and the 4 up. So that's the log of 2 to the 3rd minus the log of 5 to the 2nd plus the log of x to the 4th. Well, 2 cubed and 5 squared, because we're just going to condense this into a single logarithm, we're working backwards as to how we have been doing, it feels like. Let's just write that as the log of 8 minus the log of 25 plus the log of x to the 4th. Because when it's in a single logarithm, there's no reason to see the 2 cubed and the 5 squared. It wouldn't benefit us. So now, they're all bases of 10, so we can write a single log. The 8 and the x to the 4th were positive logarithms, so the 8 and the x to the 4th go in the top. Positive log with the 8, positive log with the x to the 4th. The 25 came with the negative log, so the 25 goes in the bottom. This is our answer. And again, if you had gone straight from here to the condensed version, you'd get the log of 2 cubed times x to the 4th over 5 squared. That's not simplified. No, there's no reason to have 2 cubed in an answer. There's no reason to have 5 squared in an answer. That's why we need the 8 and the 25. All right, so. Last second reminders. Test 3 is on right now. It's in the test section. Your review is in the homework section of my math lab. It's interactive. It's just like a homework. So you've got to help me solve this view an example. So I think that'll give you a little more practice. The review problems are similar to the test. I think there's 20 questions on the review, and I believe I made the test 15 questions. It's 2 hours, just like first and second test. You still get your 2 attempts. So there's lots and lots of availability for you to do a good job on this test. Again, the review is similar to the test. I just kind of took a few problems away, basically. I didn't want to make this a 20-question test because a lot of the problems are longer when you're doing all that synthetic division stuff. And it's not just, hey, do the synthetic division. It's part of a bigger scheme, a bigger problem, a bigger analysis, if you will. Final exam will be a week from today. Oh boy. So that's Thursday the 7th, 1 attempt only, 3-hour time limit, 20 to 25 questions, something like that. I'll ask you to submit some work in Canvas for that. Basically just pulling questions from the first 3 tests, plus a couple of questions from Chapter 4. The review is coming no later than Monday afternoon, let's say Monday by 5 p.m. I will send you an email the second it's done. Whether it's going to be a PDF kind of print off thing in Canvas or an assignment in my math lab, I have not decided yet. I'm still ironing some kinks out. But yeah. So on that note, have a good day. Hopefully everyone maintains power, stay dry, study hard, work hard. We're almost at the finish line. We can do this, we can do this, we can do this. And please make sure that you submit your official grade request via the email link that takes you to Canvas if you want an A, B, C, D, or F grade. If you don't want an A, B, C, D, or F grade, you don't have to do anything. I just default to giving you the P+, P-, or W, I think it's a WC. I don't know why it's a WC, but it is what it is, right? Email me with any questions. Have a good one. We'll see you next week. Video should be up in 30 minutes, hopefully. Fingers crossed.